All right, with this process, integration using substitution, it's necessary because there are some functions that would be extremely difficult to integrate if we couldn't make some sort of a substitution. But then once we've made a substitution, they actually become quite straightforward. Now, this is a confusing process for many students, but it'll become clearer the more you practice it. So I strongly recommend that you look at the video and go over the video a few times, that you work through the worked examples in the textbook and find out exactly what it is that they're doing in the textbook, and then you come back to the video again and then you just work through these questions one little bit at a time. And even if you're just doing one problem over and over until you can do it fluently, then you're making progress, even if it's just one question. So long as you understand the process of what's going on, then you'll start making progress elsewhere with the more complex problems. So let's start with exercise 311, question 1a, and this is the function we've got, and up to this point, the only way we would have been able to integrate this function is to expand out this 3x squared minus 1 to the power of 5 and keep on expanding it out. Just keep on expanding it out and out and out. And so that we'd have 3x squared minus 1 written out 5 times, we'd expand all of that out, collect the like terms, and then we could actually integrate the function. But that's dreadfully long and tedious. So here's what we're going to do, is we're going to use a substitution, a very common technique in all different areas of mathematics. The substitution will be, let u equal the thing that's inside the brackets here. 3x squared minus 1. That's really the thing that's presenting the problem for us. So let's see if we can deal with that and make life easier for us. Now here's the thing, is that if I'm going to let u equal 3x squared minus 1, then when x equals 0, I should write that larger so that you can see this clearly on the video. When x equals 0, then u is going to equal 3 times 0 squared minus 1. So u would equal minus 1. When x equals 1, limits are from 0 to 1. When x equals 1, then u is going to equal 3 times 1 squared, which is 3, minus 1. So we'll have 2. So as soon as I make this substitution, I have to also realize that the limits of integration are going to change. When the function was a function of x, the limits of integration were from 0 to 1. Now that the function, we're going to change this function so it's actually u is the function that we're dealing with, and that means that we have to change the limits of integration to something that is meaningful in terms of u. So the limits of integration will now be not from 0 to 1, but they'll be from minus 1 to 2. That's the first step. Well, it's the second step. The first step is to let u equal this, 3x squared minus 1. And then the second step is to redefine the limits of integration. The third step is to actually find out what is the derivative of this substitution. So du dx is equal to 3x squared, oh no it's not, du dx is going to be equal to 6x. Now oddly enough, I didn't realise this until way late in my university career. You can treat these du dx's just like regular fractions. And so I'm going to multiply both sides by dx. So du is equal to 6x dx. That's what du is equal to, 6x dx. Now what we want to do is we want to take all of this information here and somehow put it into that expression, and once we've got the right shape and form of that expression in terms of x, we can get rid of the x's and just put u's in. So off to the side here, what I'm going to do is actually still write out, it's the integration, still with respect to x, it's going to be 3 x squared minus 1 to the power of 5. Nothing's changed there yet. But see how this is an x dx. We have x dx. Well, I'm actually going to add something in here. I'm going to make it 6x dx. That is a really important part of the whole process. I'm making it equal to 6x dx. And you'll see why in a moment. But by having that 6 there, I've actually just made this thing 6 times bigger than that. So the only way to make this equal in size to that is to multiply all of this by 1/6. Okay? This 6 makes the whole thing 6 times bigger. But I need that 6x there. I really, really need it there. So to bring it back to being the equivalent size, the same size as this, I'm going to multiply it by 1/6 there. Okay, now we can do we can make the substitution, and this will make the whole integration really easy for us. Okay, so bear with me. This is now 1/6, we need that. Right, this is where we change from a function of x to being a function of u. Okay, what I do know is that 3x squared minus 1, well, that's exactly what I made u equal to. So this 3x squared minus 1 to the power of 5 is actually really u to the power of 5. So I'm going to put u to the power of 5 there. Okay, and now I also know that this 6x dx, well, 6x dx is du. That's all it is, du. So actually, that gets replaced by du. Now this thing here is really, really easy to integrate. It's very easy to integrate. But remember, we're no longer talking about functions of x, so the limits of integration from 0 to 1, they don't apply anymore. We need to have limits of integration which are meaningful in terms of u. And that's what we've done over here is when x is equal to 0, u will be equal to minus 1. So minus 1 goes in here. When x is equal to 1, u will be equal to 2. So the 2 goes in here. This will be easy peasy now. Alright, so we'll integrate that. That's 1/6 outside of u to the power of 6 on 6 from minus 1 to 2. And when we substitute in the boundaries, the limits of integration, it'll be 2 to the power of 6, or this is going to be on 6, minus 1 to the power of 6. 2 to the power of 6 is 64. And minus 1 to the power of 6 is 1. So 64 minus 1 will give us 1/6 times 63 on 6. So we'll have 63 on 36. Okay, now we've evaluated that integral. That's what we've done. We've evaluated the integral. It doesn't say that it's an area. I'm hesitant to put units squared there because it doesn't say it's an area. But that's the evaluation, and you can make it a mixed number if you want, or even a decimal if you really so desire. But probably the answers in the textbook will be mixed numbers, but they might be improper fractions like this. Alright, have a look over the video again at that. If you don't understand it, rewind it and have a look at each step by step. I'm going to do question 1E. Another interesting one. I'm going to do 3 or 4 examples, I think. 4 or 5, 3 or 4, something like that. So for 1E, we've got to do the integration from 0 to 1, and it's x cubed over 1 plus x to the power of 4, and that's all cubed, and it's with respect to x. Okay. It's this thing in the denominator which is really that's the ugly bit. So I'm going to let u equal 1 plus x to the power of 4. That means when x equals 0, u equals 1, and when x equals 1, u equals 2. U equals 2. This is going to be important for changing our limits of integration later on. The other important thing that we need is that du dx, the derivative of u with respect to x, will be 4x cubed. Okay? It'll be 4x cubed. Now, over here again, a bit of a change of colour, and we put in the limits from 0 to 1. This is actually 1 plus x to the power of 4, all to the power of minus 3. Right, I've just written that in index form. And I'm actually going to put in, down here, that means du is equal to 4x cubed dx. Now, I'm going to put in here 4x cubed dx. It's actually x cubed dx at the moment, but I'm going to put in 4x cubed dx. 4x cubed dx, but because I've made this whole thing bigger by a factor of 4, I need to get rid of that 4. I need to counteract that 4. So I just put a 1/4 out the front. And now that's counteracted. So numerically they're the same expression. And from here, we just put the pieces of the puzzle together. We have 1/4 outside of this bit here is what u is. That's 1 plus x to the power of 4. That's u. So we have u to the power of minus 3, u to the power of minus 3. 4x cubed dx is the same as du. So that's du. 4x cubed dx is the same as du. And the limits, when x is 0, u will be 1. When x is 1, then u will be 2. And now, once again, that's not a hard integral to do, is it? That's not very hard at all. We'll put the 1/4 out the front. This will be u to the power of minus 2 on minus 2 from 1 to 2. And that will be 1/4 outside of negative. I'll put all of this. I can't really, can I? So that'll be 1 on 2 times 2 squared minus the negative again, 1 on 2 times 1 squared, which is 1/4. Outside of that's 2 times minus 1/8 minus, well, it's going to be minus a minus, which is plus, plus 1/2, and minus 1/8 plus 1/2 is going to be 3/8. So we'll have 1/4 times 3/8, which will be 3 on 32. So we've now just taken this function, which looks dreadful, and we've evaluated it by making our substitution all the way through there. Let's have a go at another one. They get more interesting, and they're going to start bringing in volumes of rotation at some point in time. So I need to give you an example of the more interesting ones. Question 2a. Let's have a look at question 2a, and it's the integral from 0 to 3 of x square root sine x squared plus 1 cubed dx. And you know what, I'm going to put this into index form straight up. 0, 3, x, that's x squared plus 1 to the power of 3 on 2 dx. And it's this thing here that's inside the brackets. That's the thing that's ugly that we want to try and get rid of. So let's make a substitution of let u equal x squared plus 1. That means when x equals 0, u equals 1. When x equals 3, u equals 9 plus 1, 10. Alright, next step is, so we've figured out what the boundaries, the new limits of integration will be for the function that relates to u. The next thing to do will be to find the derivative of u with respect to x will be 2x, so du is equal to 2x dx. Okay, and this is where we're going to sidestep at this point. Right, we sidestep here. We'll put the integral from 0 to 3, still keeping it all in terms of a function of x, and this is x squared plus 1 to the power of 3 on 2 x dx. But you know what I want to do is I want to put this 2 in. I want that 2 to go in there, so I've got this whole 2x dx expression. So I'm going to put the 2 in there, which means I've just changed all of that to be a factor of 2 bigger, and to bring it back down to size, I need to put a half out the front. Okay, and that should really be an equal sign. It shouldn't even be an arrow leading into that. It's an equal sign, they're equal. Now we make the substitution. So therefore we're going to have a half, and this bit here, x squared plus 1, well, we know that that's u, so that's u to the power of 3 on 2. And we know that 2x dx, well, that's what du is. So we go du here, and the limits of integration, when x is 0, we know u is 1. When x is 3, we know that u is 10. Oops, it's not very good 10, is it? And now we'll continue with this. We'll do the integration, which will be a half outside of u to the power of 5 on 2, and we're going to put 2 on 5 there, and the limits of integration. Okay, let's substitute these things in here. That's going to be 1/2 outside of, well, the 2/5, you know what, I can take that 2/5 out too. That's a common multiplier. So I'm going to take the 2/5 here out, so it's 1/2 times 2/5 outside of 10 to the power of 5 on 2 minus 1 to the power of 5 on 2. Okay, so this is 2 on 10, which is 1/5. And this will be 10 to the power of 5 is 100,000. So it's going to be the square root of 100,000 minus 1. So root, it's 100,000 to the power of a half. I don't know what the square root of 100,000 off the top of my head is. But it's root 100,000 minus 1, all times a fifth, because this could actually be 1/5. So maybe in this case, a decimal approximation could be a good thing. And it's probably got a decimal approximation in the textbook. Okay, it's not a nice, neat, fractional, rational answer like that. This one will be an irrational number. But that's the working, and it's the same process, no matter whether it's a rational answer or not. Let's have a look then at question 7. Okay, question 7 is a really interesting one, because now they're giving you an expression to integrate, but they want a volume of revolution in question 7. So they give you this function that y equals x square root 1 plus x cubed, 1 plus x cubed, and the limits of integration for this are meant to be from x equals 0 to x equals 2, I think, yes, from x equals 2. And it's that bit in there, it's the bit that's inside the radical sign that is going to cause all the problems. This thing here is called a radical sign, in case you didn't know. The square root sign is a radical sign. So that's going to cause a problem. So how about we try and make a substitution there? We're going to let u equal 1 plus x cubed, which means when x equals 0, u equals 1. When x equals 2, u equals 9. And du dx is equal to 3x squared. So du is equal to 3x squared dx. Crumbs, how does this all work out? Well, remember, it's a volume of revolution question. So I'm just going to take you back to the last exercise. For a volume of revolution, we're going to have an expression that looks like this, an integral from a to b, and it's going to be the function of x in here, all squared dx. Alright, in this case, if we looked at that, we would have that the volume is going to equal pi outside of, and the limits would have been from 0 to 2, outside of x times 1, oopsie daisies, 1 plus x cubed to the power of a half, all squared. So that's the function of x, all squared. There's the function of x, and it's all squared. The function of x, all squared. Maybe if I put it in square brackets, the correlation is a little bit clearer between the two expressions. There's the function of x, all squared, with respect to x dx. That's what we're aiming at. Let's just maybe get rid of this power here. It's not hard to get rid of that power because there's a multiplication sign there. Again, harking back to your index laws, from 0 to 2, that will be x squared outside of 1 plus x cubed, and a half times 2 is 1, so that just becomes that expression there. Alright, I'm going to rearrange this. Pi from 0 to 2 of 1 plus x cubed, x squared dx. Now what I want is I want this whole bit here to look like that whole bit there. Those two things need to look the same. So I'm going to put a 3 in here, but I've just made that whole expression 3 times bigger than it originally was. So I put a 1/3 out the front, which brings it all back down to size again. This makes it bigger, this 3 makes it bigger, so I have to put that 1/3 there to bring it back down to its same numerical size. And now how sweet is that? We have pi on 3, this bit here in the brackets, that bit is the same as u. 1 plus x cubed, that's what u is equal to. So this is u, 3x squared dx. 3x squared dx is du. And now the limits of integration with respect to u, when x was 0, u was 1. When x was 2, u was 9. And that is probably one of the simplest integrations that you'll ever have to do. It probably is. That'll be pi on 3 outside of u squared on 2 with the limits of 1 to 9. Sorry that I've run out of space here a little bit. So we'll have pi on 3 outside of 81 minus 1 on 2, which in the end will give us 40 pi on 3? Have I done that right? 9, Yeah, 9, 2, 8, 9. Yep, 9. 81 minus 1 is 80. 80 on 2 is 40. 40 pi on 3. So the answer is 40 pi on 3. Okay, a really, really powerful tool this one is. It's a really, really powerful tool. But it's also a complex process to get your mind around at first. But once you've got your mind around it, it's just a pattern. You just follow the same pathway round and round and round. And it's not that complex. It is initially, but it's not once you've practiced it. So again, I'll leave that one with you. Work through the worked examples. Keep looking over the video and the explanations. Hopefully that is a helpful tool. And then keep practicing the problems in the textbook. All right. Have good holidays.